Thank you, Kamel. Thank you, Kamel. So it's my pleasure to introduce the keynote speaker of this morning. So I'm Yves Lepage from Waseda University. As you have heard yesterday, I'm not exactly from speech recognition, but okay, I know the names of big companies working in speech recognition. So what are these big companies? AT&T, Bell Labs, Lucent, and so on. IBM Watson Research Center. Okay, so we just summarized the career of our keynote speaker. And it's my pleasure to introduce Olivier Siohan, who is now a research scientist working on speech and language technologies at Google. Before that, he worked at IBM Watson Research Center on large vocabulary speech recognition. He worked also at Lucent Technology, Bell Labs, on broadcast news speech recognition. And also at AT&T Labs. In fact, he started by a postdoc his American career in AT&T Bell Laboratories. He is a member of the IEEE Speech and Language Technical Committee and a former associate editor of pattern recognition letters. And his research interests are, of course, in speech, speaker recognition, and his focus is on acoustic modeling and noise robustness. And he will speak about the hot topic, deep neural networks, I think. So I give you the floor, please.
Thank you. So I would like to start by thanking the organizers for inviting me here in Casablanca. It's my pleasure to be here, and especially to see so many old friends I haven't seen in so many years. So today I'm going to be talking about speech recognition and especially acoustic modeling for speech recognition, and I'm going to be describing essentially acoustic model for some of the Google's product and services that are used to transcribe hundreds of millions of voice queries every day. So before I start, I just want to give you first acknowledgement of my colleagues. I borrowed a lot of their slides and results for this presentation. And I'm going to start by giving you a very brief kind of historical overview. A very brief historical overview of the speech recognition activities at Google. So here I'm listing essentially a bunch of product and services that have been developed at Google along the years. And most people outside of the US are not aware of, in fact, the scope of the speech recognition activities at Google. So the speech team started around 2005 at Google, where Google hired a bunch of people from other speech companies. And the first product that we developed was something called Goog 411. So 411 in the US is a directory assistance. So it's a number that you dial on your phone if you need to get the phone number of a business, for example. This was before smartphones were introduced, so that was pretty much the only way you could get the phone number for the local restaurant or the local movie theater. And you would dial 411 on your phone, and typically the phone company would charge you about $1 for this call. You would talk to an operator, tell them the name of the city, the name of the business you were trying to contact, and they would connect you, connect your call. And what Google did in 2007 was to introduce a completely automated service to do that based on speech recognition. So you would just have to dial this 1-800 Goog 411 number, and you would just say the name of the state and the name of the business, or the name of the city, and you would be connected for free to the number. So that was the first product that we developed, and it was only developed in the US, so that was done by a team of about a dozen people at that time. The next big project that we worked on was called Google Voice. So this was a voicemail transcription service. Again, it's a service that is only available in the US, and what we did at that time was to give you a virtual phone number that you could use to link to your regular phone number. And when someone would call that virtual number, you could set up on the web the system so that it would ring your cell phone or your home phone or your work phone based on some rules depending on the time of the day, for example. And if you were to leave a message on that phone number, we would transcribe the message automatically, and you would get a transcript of that message in your email. And this is a product that is still being used today. Initially, when we deployed it, it was in kind of late 2009. Performance was not that great. I mean, you could kind of get the idea of what the, why someone was calling you. But there was a lot of people were kind of making fun of it and putting comments on the web because the transcription were really not that great. But today it's actually has improved quite a bit, and the performance is actually quite remarkable. In my case, I never listen to voicemail anymore. I just look at the transcript. Next, we started working on large vocabulary speech recognition for YouTube. And in fact, so when you upload a video on YouTube, it's going to be processed and automatically transcribed, and we are supporting maybe a dozen languages today. Again, when it started, performance was terrible. About half of the word were incorrectly transcribed. Today, on a typical test set, we have about 15% word error rate, so we have had significant improvement over the years. And then what really started around 2012 is pretty much the flagship product at Google for voice, which is voice search. So this was developed on your cell phone so that you could make a vocal query on your cell phone. And this became a very popular service. I'll describe in a minute the number of languages that we support for that product. And more recently, we did a lot of work on Google Home, which is a smart speaker. So it's a very small speaker that you can put in your home, and then you can control by voice. So it's quite a different challenge as far as speech recognition is concerned, because here we're talking about far-field speech recognition. The microphone is a couple of meters away from you, so you have to deal with noise and with reverberation in the room and stuff like that. So it's a much more challenging problem, and I'll describe how we address that problem. And last, now we are working a lot on something called Google Assistant, which is the virtual assistant. So yesterday there was a talk about those virtual assistants. So this is now becoming a very important focus for us, and we are developing speech technologies for that. To give you an idea of the scope of our activities today for voice search, we cover about 120 languages. If you've ever built a speech recognition system from scratch in one language, I think you can appreciate the amount of effort that is needed to build so many systems. So today I'm gonna give you a bit of an overview of how the technology has evolved along the years, ranging from what I call the classical speech recognition, which was based on HMM, to now the use of deep learning for speech recognition, which is now the dominant approach for speech recognition. So I apologize for the next couple of slides are going to be very simplistic slides about speech recognition. So if you're very familiar with speech recognition, you're going to find this a little bit boring, I'm afraid. But if you're not familiar with speech recognition, I think you're going to find the last slide of my presentation maybe a little bit confusing, but hopefully, on average, everyone should be somewhat satisfied with, hopefully satisfied with the slides. So essentially here, I'm only going to be talking about speech recognition. I'm not talking about understanding or anything like that. And the problem we're trying to solve is that you have audio as input, and we just want to produce a corresponding text. And this is typically an ASR system. Typically consists of multiple models. There's an acoustic model that is used to convert sounds to phoneme, where phoneme is like the spoken alphabet, if you like. Then we have a pronunciation model that is used to convert phoneme into words. So here, for example, you have the sequence of phone corresponding to the word your, which is mapped to either the determiner your, or the sentence you are, or the contraction of the sentence you are, which have the same pronunciation. And then you have a language model that is used to disambiguate sentences. So for example, if you have the combination your book and your book, the language model is going to tell you that your book is much more likely than your book, okay? So more formally, if we want to look at this with the formula, this is a fundamental equation of speech recognition. And what we're trying to do is that we have an audio waveform O here, and we are trying to find the word sequence W that maximizes the probability of a word sequence W selected from a very large set of word sequences. And the one that has the maximum probability is the one that is going to be recognized by the system. And if you use the bias rule, you can now split P of W given U as a product of P of O given W times P of W, and P of O given W is the acoustic model, and P of W is a language model. And the argmax of W, which is essentially the search process, you have to enumerate a very large set of possible sentences and select the one that is going to maximize this quantity. And this is going to be the output of the system. So, and just to make it clear, the way we measure performance of the speech recognition system is just the word error rate. So we just count the number of errors. So suppose that the reference transcription for a given sentence is the cat is in the hat, and that the system transcribes this as the cat in the bat. You have an extra the that is inserted, so that's one mistake. You have is that has been deleted by the system, that's another mistake. And you have the last word where the system recognized bat instead of hat, that's another mistake. So we just accumulate the errors and divide by the total number of words in a reference. In this case, it would give us a word error rate of 50%, so half the words are wrong. And so typically, to evaluate a system, we have test set of about 15 hours or maybe more. We use typically a couple of test sets per language, and we compute the word error rate on those test sets. And that's how we evaluate systems. Of course, there are some extra consideration for production system. The system has to be fast, and it has to have low latency and this type of things. So why is speech recognition difficult? Well, it's difficult because you have to deal with contextual effect, and especially co-articulation. So if you look at the word bat versus butter, the T sound is, for most American speaker in butter is going to be pronounced almost like a D, while in bat it's really a T. So just based on the context, the same phone is going to be pronounced differently. If you look at the sentence, how do you do? The two do are pronounced differently. The first one is, how do you do? So it's almost entirely deleted. And if you look at the sentence half and half, the and word in the middle is not going to be pronounced as a canonical pronunciation for the word and, but it's going to be more like half and half or something like that. There's a lot of variability in a speech signal as well. Some of it is between speaker variabilities because people have different accents, they have different type of speech. The gender and the age affect the variability of the signal. There's also a lot of within speaker variability. The speaking rate can change, the vocal intensity can change. The speaking style, spontaneous speech versus read speech is very different. So you have to account, you have to be able to model all these sorts of variability to build a system. And another source of variability is the environment. If you're talking to your phone by holding your phone, it's very different. The acoustic variability is very different compared to a smart speaker that is in your room, which is going to capture a lot of noise. So you have to deal with that. And last, speech recognition is essentially a search problem, and you have to search through a very large space of hypotheses. So large speech recognition means different things for different people. But when I started working on speech recognition, 20 years ago, 25 years ago, large vocabulary speech recognition meant vocabulary size of about 1,000 words or something like this was considered as large vocabulary speech recognition. Today, in a system like Google Voice Search, the vocabulary size is about 5 million words. So imagine the number of 3-word sentences that you can cover when the vocabulary is 5 million. So the search space is extremely large. So I'm going to give you, here briefly a brief history of speech recognition. So I'm going to just discard completely what happened in the 60s, which was not based on statistical techniques. And in the 70s, this was the beginning of really modern speech recognition, where people started working on statistical speech recognition. And this pretty much was the dominant approach from the 70s to around 2010. And then in 2010, something happened, which was like the emergence of deep learning, and essentially deep learning kind of took over the acoustic modeling for speech recognition. And this was really a breakthrough, and suddenly in a space of a couple of years, we saw the word error rates drop significantly, sometimes by 50% maybe in just a couple of years. So what I'm going to do today is essentially describe this transition from the classical HMM-based system to some of the more advanced modeling techniques based on deep learning that we're using today. So classical speech recognition, so essentially it covers a period of 40 years, more or less. And I'm just here listing the main point of how classical speech recognition worked, and I'll be describing in more detail some of those points in the next couple of slides. But essentially the idea was, first you had to do some kind of feature extraction, and typically this was done every 10 milliseconds. We would compute some features by doing some form of signal processing. So typically we would extract some kind of spectral feature from a speech signal. We would then decompose the words into elementary sounds called phones using a phonetic pronunciation dictionary. Acoustic models were based on a generative view of speech, and especially speech was treated as the outcome of a stochastic process modeled by a hidden Markov model. Language models were based on n-gram language model, which means that given the n-1 previous word, you're trying to predict the next word. This is what an n-gram is. And the two sources of knowledge, the acoustic model and the language model, were combined into a very large graph that is used to drive the search, on which we would just find the minimum path, and the sequence of words along that path is the recognition hypothesis from the system. So very quickly here, the feature extraction was just classical signal processing. We would just take the analog signal, turn it into a digital waveform by sampling it, typically at 16 kilohertz. Then we would do some form of windowing, and every 10 milliseconds we would extract some kind of spectral features. And usually the dimension of those features would be between 40 and 100 every 10 milliseconds. The big assumption at that time was that the feature vector are assumed to be the output of a generative process. So what it means is that the stochastic process here is represented by a hidden Markov model. So a hidden Markov model is some kind of stochastic machine. So it's a bunch of states and arcs. The transition between the states are probabilistic, and in each state you have a probability density function. And the idea is that you have a little token here that's going to do a random walk through that machine, and whenever you enter a state, you draw a sample from the probability density function associated to each state, and the assumption is that the speech process is exactly modeled by this type of model. So here, imagine this little white token here enters the first state, then you draw a sample from that first state, it gives you the first frame, and then this token, this red token, jumps from state to state. So here it's going to stay in the first state for a couple of frames. Every time you sample a frame from it, and then it's eventually going to jump to the second state. Again, every time you enter a state, you sample a feature vector, and so on and so forth. The assumption is that the observation have been generated by this type of process. And what we want to do, the problem of acoustic modeling, is to estimate the parameter of the probability density function that are associated to each state. So now, assuming that you have this model, let's assume we have a model for the word W, and assuming that you have a sequence of feature vector X, what we want to do is to compute the likelihood that this sequence of feature vector has been generated by this model, W. So the way to do this is that the issue is that we don't know which state generated what frame, so we have to enumerate all the possible segmentation of the sequences of frame into the underlying sequence of hidden states. And if you do that, then we can compute the likelihood of the sequence of feature vector, and it is defined as the sum over all the possible segmentation of the P of X given the segmentation times the likelihood of the state sequence. And we use a very important assumption, which is a conditional independence assumption of each frame. So the likelihood of the sequences of frame given the state sequence is just the product of the likelihood of each frame given the state it's coming from. And again, now when it comes to modeling the probability density function associated to each state, the way it was done was to use a mixture of Gaussian densities, which is just represented as a weighted sum here of normal distribution. So, so now the way to build those models, to train those models, is that we have to essentially assign a state ID to each frame. And so this is done by doing something they call Iturbi alignment. So suppose that you have a model for the word sequence W, and suppose that you have a training sentence, so just a sequence of frame here corresponding to that word sequence. What you have to do is Iturbi alignment, which is a process that is going to assign a state ID to each frame. And once you've done that, you can just collect together all the frames that are, all the feature vectors that are labeled with the same state ID, and you just estimate independently the parameter of the probability density function associated to that state. So this is a very efficient way to do this. And this is how acoustic models have been built up to pretty much 2010. And then typically you would just iterate this process, and as you iterate, the likelihood increase, and you are essentially doing maximum likelihood estimation of the model parameters that way. So now, in a previous slide, I showed that, well, we were dealing with a word acoustic model, but in fact, this is not what we do. And the question is, well, what makes a good acoustic model or acoustic unit? So it has to be trainable, which means that the acoustic unit have to occur sufficiently enough in your training data so that you can estimate them. So subwords units are typically good, and words units are typically bad because you don't have enough occurrences of words in your training corpus in general. Though I'll be talking about some system where you actually do use word-based model when we have a lot of training data. It has to be generalizable, which means that you have to be able to represent any kind of sequence of words. So this means that subwords units are good because you can just concatenate them in whatever order you want to construct words. And they have to be invariant to the context, to the phonetic context, which means that we're going to typically use context-dependent units that are conditioned on the previous sound and the following sound. So because of that, people have been using context-dependent phone units for a very, very long time. So to summarize, so we are essentially decomposing words into a sequence of context-dependent HMM states. So here, let's assume that the word is the word call. It is decomposed into the sequence of phone K, O, and L. Then the sequence of phone is going to be decomposed into context-dependent states. So the context-dependent phone, so the O in the O in the middle of the word is going to be conditioned on the previous phone, that is K, and conditioned on the next phone, that is L. So we're going to have different version of O based on what's before and what's right after. And then because a phone is actually still a fairly long unit, the statistical property of a phone are different in the beginning, middle, and end of the phone. So we're going to split this into multiple state or multiple parts, and we're going to use typically a three-state HMM, where we're going to have a different probability density function for the beginning of the phone, the middle, and the end. And again, the assumption is that the speech signal is then generated by sampling frames for the sequence of HMM states. So now that we are modeling context-dependent states, and one of the main issues in the classical speech recognition was to control the size of the inventory of HMM states. And the issue is that, well, if you look at a language like American English, you have about 42 phones. So the total number of context-dependent triphone is going to be 42 cubed. And if you have 3 states per phone, you're going to have 3 times 42 cube states that you have to model, and this is too large. So what we typically do is that we're going to cluster together states that occur in similar contexts. So on the left here, you have a bunch of HMM for different context-dependent variant of the phone O. And you can see that on the right, we have a clustered version of it where we cluster together states that have similar properties. And they are very well-known algorithms to do that. And essentially, that's the way speech recognition was done up to roughly 2010, 2012. All the systems were based on this type of techniques. And what happened in around 2012 was that deep neural networks started to take over. And in fact, it was a little bit of a rediscovery of deep neural network, because in the mid-90s, a lot of people had been working on neural network as well, but at that time, people had limited amount of data, limited amount of computing power, and the deep neural network didn't really work that well. But in 2010, things started to turn around. And the idea of using neural network to build acoustic model is the following. So instead of trying to estimate the parameter of probability density function, we're trying to estimate the parameter of classifier. And so on the left, you have the GMM HMM model, where again, you have a sequence of frames that have been labeled by the state ID. And what we are doing is that we're trying to estimate the parameters of the Gaussian mixture model corresponding to each state ID, and this can be done all in parallel. It's all independent. All the states are independent of each other. But if you use now the DNN type of model, what we are trying to build now is a neural network where the input is going to be a sequence of is going to be frames, and what we're trying to do is to predict the correct label associated to each frame. And what we end up with is a neural network. So deep neural network essentially are used to predict the class label associated to an input feature. So here, let's take this simple example here where we have 3 classes, the red, green, and blue classes. And at time t, the frame xt is of class red. So we have 3 outputs, and what we would like is that this network should predict a high probability that the state at time t is red given the input frame. So on the input side, typically X is going to be log spectrum computed over 40 to 120 filter bank or something like that. Often we stack frame together to take context into account. In our case, when we're working on deep neural network, we would typically use a fairly large number of frames. We would stack something like 26 frames together, so that's about 250 milliseconds. So it's a duration of a syllable more or less. And based on this, the stack feature vector, we would just try to predict the identity of the corresponding context-dependent state. In the middle, you have a bunch of hidden layers, and as people we talked about yesterday, the hidden layer, the hidden node, the node just do a weighted sum of the inputs, we typically use rectified linear units as activation function. The use of rectified linear units is actually believed to be one of the reasons why it became much easier to train a large neural network as opposed to using a sigmoid type of activation or hyperbolic tangent type of activation. So rectified linear units are much more effective when it comes to training very large model. And last, we have a so-called softmax layer. So given the activation A of the last layer, we are just computing this quantity that is used to map the activation into a probability domain, so that what you're predicting at the end is the probability of a state given the input feature vector. And a conventional DNN training is done to minimize the cross-entropy loss. So here on one input example, the input example at xt is xt, and let's assume that the reference label is the red label again. So the label is represented as a hot vector, one hot vector. So it's a 0, 1, 0 here representation because the second class is a red class. And let's assume that you feed the neural network with this feature. The neural network is going to predict whatever it predicts here. the y hat prediction. And the objective of the training is to minimize the cross-entropy loss, which is defined here as the sum of the reference label times the log of the predicted label over all the possible label. And the way we optimize those models is just using stochastic gradient descent. So we compute the gradient of the loss with respect to the model parameter, and we just do an update based on gradient descent. And essentially, that's the way we train model. So that, as I said before, though, this is not new, and the way the DNN acoustic model were used in the mid-90s. But in 2010, when people started looking at it again, what really was different was that we started using much more hidden layers, so typically more than 6. So at Google, when we were building DNN, we were using something like 8 hidden layers with about 2,000 nodes per layer. So these are big network with about sometimes as many as 100 million parameters. We would try to predict context-dependent states unit, while in the mid-90s, people were typically just predicting context-independent state units. We are typically doing training using thousands of hours of training data as opposed to tens of hours in the 90s. And we use much more efficient hardware nowadays. So the way we do stochastic gradient descent at Google is a little bit special. We do asynchronous stochastic gradient descent, which enables us to run, to train neural network in a distributed manner. So the way it's done is that we have a parameter server that holds the model, so all the matrices, and we split the data into subsets. So we do data parallelism, and then we have a bunch of model workers that are gonna run inference to compute the prediction and do back propagation to of the gradient. And once you have the gradient, you ship the gradient to the parameter server that is going to do the update, and everything is done in parallel, and it's done in a lock-free mode, which means that sometime you're going to be overriding something, and it doesn't really matter, because the idea is that if you process a mini batch, you're dealing with a kind of a sparse update of the model parameters, and because the update is sparse, it doesn't matter if from time to time you're overriding the parameters. And at the end of the day, this enables us to run training on many, many machines, and we can efficiently train models that way. So once you've trained those models, at the end, everything else is the same as when we were using GMM-based system. The only thing you have to be able to do is to compute the likelihood of a frame given the corresponding state. So with GMM, we would just compute P of X given S from the Gaussian mixture models. But with DNN HMM, what the network predicts is the probability of the state given X. So we have to use Bayes' rule to flip things around. And at the end of the day, we are just essentially scaling the prediction from the neural network by the state prior. And this is what we use to run decoding. There are some kind of technical details that actually are quite important to make it work, that you typically have to scale down the state prior, and especially you have to scale down the probability of predicting silence. It's typically a big deal to make it work. And the use of DNN led to very large performance improvement. So here the numbers don't matter that much. I'm showing you the word error rate on about 30 different languages. And this was from several years ago, 2012. So the blue is a DNN-based system, and the red is HMM, classical GMM HMM-based system. And you can see that we got something like between 10 and 25% word error rate reduction by moving from GMM to DNN type of models. So the issue with using DNN is that essentially DNN are stateless, and they are not very good at taking into account temporal dependencies in the input. So as I said before, the way we handle temporal dependencies is by stacking adjacent frame together. So if you run feature analysis on your signal at every 10 milliseconds, you end up with a sequence of frame here at the bottom. And what we do is that at time t, we're just going to stack together a couple of frames that were right before and a couple of frames that are right after. And this is what we use to train the DNN. And as I said before, we can stack a fairly long sequences of frames, sometimes up to 26 frames are stacked together. And the DNN is pretty good at dealing with this fairly high dimensional input feature vector. But essentially what the DNN predicts is P of yt given xt. And there's no explicit modeling or implicit modeling of the temporal dependencies. So what people did next was to introduce state in the neural network by using recurrent neural network. And the idea of a recurrent neural network is that we have a loop that allows to propagate information from time t to time t plus 1, so the past affects the future. And as I'm going to show in the next couple of slides, this led to additional improvement on our system. So with an RNN, you can unfold the RNN across time or a long time, like on the picture here on the top left. So this kind of represents the temporal dependencies of the input to the output. And the good thing about RNN is that they can learn short-term dependencies. So if you look at the middle picture on the left, the frame 1 and 2, for example, are going to affect the prediction at time t equals 3. But remember that this is trained using stochastic gradient descent. So you have to do back propagation through time. So when you're in state number 3 and looking at the prediction at time 3, you have to propagate the gradient back to the beginning of the sentence. And this is done by using the chaining rule. So you keep multiplying gradients over time. And as the sequence gets longer and longer, the gradient, the product of the gradient, which are typically small number, essentially becomes smaller and smaller, and the gradients vanish. And the result of that is that you cannot learn long-term dependencies with classical recurrent neural network. And what was introduced, in fact, in the mid-90s is something called LSTM for long short-term memory network. And the LSTM is a little bit different, but it introduced a cell state that can be propagated a long time for a very long duration. And this is what is represented here. The cell state here flows here on the top, and it flows pretty much unchanged a long time. And because it's not changed much, it enables you to back propagate the gradients over a very large number of time steps. And because of that, the LSTM are very good at learning longer term dependencies that are needed for speech, because we want to model the time dependency maybe 20 frames back. So the use of LSTM led to, in fact, significant word error rate reduction over a DNN type of model. These are some older results from 2014. And at that time, we were using roughly 2,000 hours of training data. And by unrolling the LSTM over 20 time steps, we were getting something like 10% error reduction over DNN. So LSTM at that time became like the kind of models that we were using. Let me see, maybe I should skip this. So sequence training. So far I've been talking about cross-entropy training of model, where what you're trying to do is at time t, you have some feature and you try to predict a corresponding label at time t. But this type of training doesn't guarantee that you're going to minimize the word error rate. So because it's not related at all to the word error rate. So in the mid-90s, people developed something called sequence training, which is a criterion to optimize your system that is more directly related to the word error rate. And there was a lot of word, even way before the 90s, it was developed for discrete HMM, and it became very popular in the mid-90s, especially following the work from Dan Povey, where he essentially explained or described how to make sequence training work in a very systematic fashion in his thesis, and everybody started getting good results with sequence training. So the idea of sequence training, you can just, you don't need to read, but the main idea is that if this is here the reference sequence of state, And if no, you take your model and you run recognition with your model and construct a lattice that is going to, a lattice is just a sequence of state representing multiple competing hypotheses. What you want to do is optimize your model so that the sequence, the reference sequence of state in your lattice, so the sequence of state that corresponds to this, to this line here, you want to maximize the probability of that sequence here and minimize the probability of any other competing sequence. And if you do that, you're doing something called sequence training, and this again typically leads to a very large reduction in word error rate, something like 15, 20%, 25%. And what wasn't clear is how to apply this kind of technique to neural network. But again, around 2009, people at IBM started working on this, and at Google as well, we started working on this, and we came up with a formulation to do this. The main idea is that you can just, when you compute the gradient of the loss, again, by applying the chain rule, you can compute the gradient of the loss with respect to the activation of the last layer of your neural network, and then by the chain rule, you then compute the gradient of the last layer with respect to the model parameter. So the first here, derivative here is what we call the other derivative. So it involves running decoding and computing the derivative of the loss function with respect to the sequence of state. And the second derivative is the derivative that is backpropagated through the network. I'm just going to skip this. But again, this thing led to something like 15% at least error reduction on very large test set. And we are able to also run this type of training in a completely distributed fashion. But I want to next talk about something called CTC, that is Connectionist Temporal Classification. So this was a training technique that was introduced by Alex Graves in his thesis in 2006, and that eventually was applied to speech recognition at Google. And originally, we got very excited about this type of technique. So the idea is that we want to train a neural network to directly predict a sequence of labels. And let's assume that you have a sequence of 7 frames here, x1 to x7. And what we would like to learn is directly learn the corresponding, say, sequence of phones. Let's assume the sequence of phone here is ABC. And the problem is that on the input, you have a sequence of 7 frames, but on the output, you only have 3 frames. So how do you go from a sequence of length 7 to a sequence of length 3? And the problem is that, well, if you present 7 frames to a recurrent neural network or a DNN or whatever, you're going to have 7 predictions. But here you just want to predict ABC. So what do you do? And essentially the way to handle this is that, well, we're going to introduce some kind of dummy symbol, some dummy prediction that means I don't know, and we're going to call this a blank symbol. And the idea is that to train the model to predict ABC, in fact, we're going to train it to predict some equivalence class of ABC that is going to be represented by this regular expression here that is going to be blank star A plus, blank star B plus, blank star C plus. So it corresponds to any sequence of blank, followed by 1 or more A, followed by any number of blank, followed by 1 or more B, followed by any number of blank, and 1 or more C. And again, any number of blank. So we are going to train the neural network to predict any possible way of representing the sequence ABC by kind of stretching it and adding blank in between, okay? And now if you, and the way to kind of read the prediction is going to be, suppose that the neural network predicts the sequence here, A blank, B, B blank, C, C. We're going to discard repetition, and we're going to discard the blank symbol, and that gives you the predicted sequence. So the way those models are trained is to maximize the likelihood of all possible way of labeling the target sequence. So again, if we want to learn or to train the model to learn the sequence ABC, we're going to in fact train it to learn all the possible way of expand ABC by introducing a blank in between. And if you take one of this sequence here that I call one labeling of the target sequence, we are just gonna the loss function that is used is just to minimize or maximize the probability of the label sequence given the input. And CT, so if a label sequence here corresponds to say one of those sequences, and we're just summing over all the possible sequences. And again, CTC rely on the conditional independence assumption of the output. So the likelihood of a sequence of labels given the input sequence of feature vector is just going to be the product of the predicted label given the input feature vector. And this can be, again, estimated using forward-backward. Quickly here, the essentially maximum likelihood of cross-entropy training of a classical HMM and CTC training, it's based on the same forward-backward procedure. The only difference really is the fact that we know we are enabling blank to occur and repeat itself any number of times between each label. But essentially, the training procedure is very similar compared to classical kind of cross-entropy training. What's interesting with CTC type of model is that the model is going to predict labels in spike. So if you look at the output here over time, so this is the predicted label or the posterior probability of each label, each label over time. This is with a model that is trained using cross-entropy. So you can see that at the beginning here for the first several frames, the probability of this is probably silence is close to 1. And then you have the probability of each possible class. And then at the end again, you have a probability for silence that spans many, many frames. And everything is kind of overlapping. But if you look at now a CTC trained model, what you can see is that the model most of the time predicts blank. And from time to time, it just predicts the label that you're trying to learn. And in fact, you can pretty much read the sequence of phone just from the spikes. So this is a kind of very interesting behavior. And I have a little movie here. I don't know if I'm going to be able to play this. Well, somehow no. Well, I can play the movie, but the movie here was supposed to show you how the spikes start to appear as the training progresses. So initially, when the model is randomly initialized, the only thing that is predicted is blank. And then suddenly you see the model starting to output, to spike, predict its prediction. And what's interesting is that the spikes are completely desynchronized with the input signal. Oh, here it's now starting. Okay, so here it is. Well, I don't know if it's. I'm not sure it's going to start. So yeah, so here at the beginning it predicts only blank, and then suddenly you see the spikes that start to occur. And what's interesting is you're going to see that the spikes are moving along quite a bit. So here, this spike here corresponds to the H sound. Here, the sentence is, how cold is it outside? So this first spike here is the H sound. And at the bottom, we show the alignment, just essentially where each phone occurs. And you can see that the prediction for H sometimes occur 2 or 3 phones after H, after the phone was spoken. So there's completely asynchrony between the prediction and the input. Okay, so this continues and so on and so forth. I'm going to stop it. Let me go back to. And we found out that to make CTC stable, we had to use first a lot of data. We use something called multi-style training. I'll talk about it in a couple of slides. So we use some technique to generate artificial data. So by perturbing the training data a little bit, and this enables us. I have to speed up. I have so many other slides. Anyway, so. CTC works very well. Some issue is that sometimes the prediction occurs completely at the end of the sentence because you have, since there's no constraint, you're better off waiting and waiting and waiting before starting to output prediction. So we have to deal with this and introduce some constraint that spike occur in a specific time, at a specific time interval. Otherwise, there's a lot of latency in the system. But I'm going to skip this. Initially, we are very excited with CTC training because we thought it was significantly better than regular cross-entropy training. I think some of our latest results suggest that, in fact, CTC and cross-entropy perform as well. Something I forgot to mention in a previous slide is that one interesting aspect of CTC is that We are not modeling context-dependent state, we're modeling context-dependent phones, and because of that, we are using single-state HMM, and we are computing the feature vector at 30 millisecond frame rate instead of 10 millisecond. And this was a very big deal for us because suddenly we reduce the computational load by a factor of 3. So given the amount of machine we use, when you can save 3 times the computation, it was a very, very big deal. But at the end of the day, you can train a low frame rate model operating at 30 milliseconds with cross entropy, and it pretty much works as well as CTC. So today, our model, our LSTM model trained with CTC, but LSTM trained with cross entropy work as well. And in both cases, you can follow this with sequence training to improve even further the performance. A quick word about multi-style training. I'm going to kind of rush through those slides. Imagine you have to build now a system for a device that is on the table. So this is for speech recognition. The problem is that we don't have data to train model. We only have data when people are talking on the phone. So what do you do? How do you initially construct your system when you have nothing, right? And what we did was to construct some kind of room simulator. And the idea is that we built a simulator where we can model the position of a speaker in a room. We can model noise sources. We can model the number of a microphone that are going to be in that room. And then we essentially probabilistically sample some of these parameters, the location of the speaker, the reflection coefficient on the wall, the size of the room, and so on and so forth. And we process the voice search training data by sending it through this thing, and we simulate a number of microphones. And that way, we were able to build very large training set for multi-microphone type of data. This had a big impact on the performance of the system. Here, quickly, I'm showing you here on the right the performance of a baseline system that was trained on regular voice search data, and each line here corresponds to different test set. And this is so this is a word error rate on different test set, noisy test set. And this is what happened when you use a room simulator to simulate this type of noisy condition. And we got like tremendous error reduction by just doing this type of brute force technique by corrupting the training data to make it noisy and to retrain model from that. I'll skip this. YouTube is an interesting case. For YouTube, we have a lot of data. When you upload a video on YouTube, you can also upload the transcript. And a small fraction of people do that. They upload the transcript. And given the amount of data that is uploaded in YouTube, if we take the transcript and do some form of lightly supervised training, as was described yesterday, we can end up with very, very large training set. And in particular, we constructed a training set of about 125,000 hours of training data. And this is what we use to train our YouTube model. And does it matter to use that much data? So here I'm showing you the performance that we got by increasing the amount of data. This was a baseline system trained from 650 hours of supervised data. We had something like 30% word error rate. And as we increase the amount of data from 650 to 125,000 hours of data, we pretty much half the word error rate, and now we're getting something like 14% word error rate on YouTube. Given that we have so much training data, is it possible to reduce the vocabulary size so that we can do whole word type of model? So this shows the impact of the vocabulary size on the out of vocabulary rate. So by default on YouTube, we are using 500,000 words vocabulary, and this led to 0.23 out of vocabulary rate and a word error rate of 14.2%. What happens if you use a much smaller vocabulary, let's say about 80,000 words? Well, if we use 80,000 words, the out of vocabulary rate jumps up. It goes from 0.2 to 0.6, but the word error rate doesn't increase that much. It goes up to 14.7, which means that it becomes possible to train whole word model for YouTube. And this is what we did. We built whole word model using LSTM, bidirectional LSTM, trained with CTC on YouTube. And the good thing is that since this is producing this type of spiking behavior, we directly, if you just read the spikes, you get directly the decoded sequence of words. So here, the advantage is there's no decoder really involved. You just run inference to your neural network, through your neural network, and it gives you the sequence of words. There's no lexicon involved because we are predicting directly words. There's no context-dependent model or nothing like this. It is a very simple system, and this thing runs extremely fast. We can get this thing running at a fraction of real time. Here, I'm showing you the results with word model, and you can see that, in fact, word model perform better than context-dependent phone model. Without a language model, we get a performance 13.5% with this type of model. So just sending the data through the LSTM, there's no language model, and it performs better than a model that uses a language model. I have to, can I have 5 more minutes? Because I want to quickly talk about end-to-end models. So the hot really topic in speech recognition nowadays is something called end-to-end model. So the idea is that we want to replace all the different components of a system. So the acoustic model, the context dependency model, pronunciation model, verbalizer. Verbalizer is what lets you go from written domain to spoken domain. Language model and eventually second pass language model that are used for rescoring. We want to replace this with a single acoustic model, or a single model that's going to do everything. And so you can do this with CTC by trying to predict grapheme, but this doesn't work at all. It's terrible. CTC predicting grapheme is terrible. But the way to fix this is to use something called an RNN transducer. And I'm going to skip a lot of those slides here. And this here summarizes the different type of sequence-to-sequence model that people are looking at. So with CTC, you have a sequence of input feature vector, and you want your model to predict the correct label at time t, given all the frames observed up to time t. And here the labels are going to be character labels. With an RNN transducer, the big difference with CTC is that the prediction is going to be conditioned on the previous labels that have been predicted. So P of YT, given the sequence of feature up to time t, is also conditioned on the previous label. And this is what made this type of CTC model on grapheme works, by introducing this dependency on a previous label. And as soon as you train a model that introduces dependency on a previous label, well, it becomes kind of a language model as well. So you're essentially merging together a language model and an acoustic model and jointly training them together. There's more complex form of sequence-to-sequence model that are called the listen, attend, and spell model that condition the output on the entire input sequence of label. One issue with this is that this is not real time, because you have to observe the entire sequence of input in order to do the prediction. Just quickly, the way this type of RNN transducer operates is as follows. So you have an encoder that is similar to some kind of acoustic model, and you have a decoder that is similar to some kind of language model. And at time t, you present a frame, so an input feature vector on the encoder, and you present the beginning of sentence symbol to the encoder, and the output is going to be the label that you want to predict. So typically we use character, and plus a blank. So if the network predicts a blank, you advance and go to the next frame in the encoder, and you stay in the same state in the decoder. Now at time t plus 1, you're still predicting blank. Now suddenly, at time t, you're predicting the G label, and you're going to now propagate this G label on the input to the input of the decoder, and so on and so forth. You keep propagating the output label back into the decoder, and whenever you predict a blank, you feed the next input frame to the encoder, and this predicts essentially the sequence of letters. There's some training procedure that is very similar to CTC training, and if you look at the performance of this type of model, these are very recent results from my colleagues. This is on dictation type of task. This is on voice search. These are the classical CTC style model trained on context-dependent phone. You can see the performance around 5–6% where their rate, maybe a little higher for voice search, and this is just on numbers only in voice search type of query. And you can see that the performance of different classes of sequence-to-sequence model that are trained to predict letters is very good. In some cases, we're we are very close to matching the performance of a more traditional CTC type of system. On numerical entities, we're actually doing much better. So we have a lot of activities related to this type of model. If you look at the next ICASP, we submitted something like 10 papers just on those areas. And essentially that's it. So deep learning led to, through the use of massive data set, large computing power, there was a real breakthrough in acoustic modeling. We are seeing that sequence-to-sequence models are becoming competitive with the traditional independent AM language model and search type of paradigm. Currently, the appeal of a sequence-to-sequence model is that we're getting rid of verbalization, we're getting rid of lexicon, and we are jointly optimizing everything. And we believe that this is kind of the way to go in the future to build acoustic model. Thank you.
So thank you very much. I think everybody is satisfied, the specialists of speech recognition and the less specialists like me. We have some time for questions. This will, then we drink less tea, but...
I can start. Thank you very much, Olivier. I'm very proud to be your PhD director, you know. Well, there has been a lot of publication of speech recognition system using raw data as input instead of Fourier transform or NFCC or whatever else. How do you elaborate a little bit? Are you using this kind of system or not? Yeah.
So on those devices, you have multiple microphones. So we spend a lot of time first using signal processing techniques like beamforming and this type of things to try to improve the quality of the signal. And we were very unsuccessful with those techniques. At the end of the day, we ended up doing some kind of beamforming, but directly within the neural network. And this is like actually this yellow block here. So we use only 2 microphones. And the interesting part is that we use, so the input layer does a complex Fourier transform, and it is followed by a complex linear prediction. And you can show that this is equivalent to doing filter and some beamforming in the network where you're learning the parameter of the filter automatically. But we also did some work where we would directly feed the raw waveform as input. And we eventually found out that it performed pretty much as well as using log spectrum. But since performance is pretty much the same, we still kind of stuck to using log spectrum. But indeed, you can now also completely discard the front end or the traditional front end and feed directly raw waveform to your network and get good performance.
Can we?
Thank you very much, Olivier. For this presentation, I was very impressed by the quantity of data, because it is Google's 125,000 of hours for training the model. So it is very difficult today to do research against Google in speech recognition. I'm impressed also because I use Google, the speech recognition of Google, and I'm impressed by the recognition of unknown words, which I consider proper names, for example. Could you give us details about how it can recognize Vendœuvre les Nancy, for example, which is, I suppose, it is not a known word?
No, it is. The vocabulary is very large, right? So we...
500,000.
No, so 500,000 is for YouTube, because YouTube is, it's kind of classical dictation. So for American English, with 100,000 words, you cover pretty much, your regular conversation, everyday conversation, or even newspaper type of, or broadcast news type of speech. For spontaneous speech or voice search, in English, we use a vocabulary of 5 million words. So it's a very, very large vocabulary task. And that's why we can handle any kind of named entities that well. In addition, we do a lot of, in this type of product, we also do a lot of dynamic expansion of, say, your context list in your phone so that you can call people. So a lot of stuff happen based on what's in your phone. We expand the vocabulary based on that. There's a lot of tricks that we do to make these things work very well.
Does it mean there is a specific vocabulary for each user?
There's
the global vocabulary plus something small, depending on the,
There is some, that's right, for just based, say, on your contact list.
The content of your mobile phone.
And it happens on the phone.
Maybe we could take a last quick question. If not, I would have a question, which is a question from the researcher's point of view. Okay, you have an enormous amount of data. You speak about training networks, neural networks on that, and using specialized hardware, right? Yeah. So, okay, for somebody building a product, so you train once and then it's done, and okay. But from the researcher point of view, you need to do some experiments, right? Several experiments. So my question would be, how long does it take to train any of these innovative techniques on such large amount of data, and in number of hours or days? Or
I think maybe Mohammed can comment better than I can.
So for production, typically we train CDC models, typically we train them for 5 days. And that's, I mean, if we let them train for more, for longer than that, we might get like maybe another 0.1 reduction in word error rate. So 5 days is typically the number. For experimentation, we don't have to wait for 5 days. I mean, like if you're just comparing this method to this method, you can just train for, let's say, 1 day, and then not 1 day, I mean like, but for less amount of time, but you can just make it like equal amount of time for both methods in order to compare.
But still on a large number of GPUs? Or
yes. Because otherwise two things. It's not a fair comparison, and you're not utilizing all the power that you can. You're not getting the best number that you can from all
Thank you. Thank you. Yes. Thank you very much. So we will close this session, and we'll go for the coffee break. Thanks again to Olivier. Thanks a lot.
Thank you very much, Yves, for chairing this session. Maybe just a last detail for people who would like to have an attestation of participation. You can find it during the coffee break. So ask the organizer.